students, today we will discuss about Cauchy's integral theorem. Before going to Cauchy's integral theorem, we will discuss the definitions for simple and multiple connected regions. First definition is simple curve. A curve which does not intersect with itself is called simple curve. A simple curve which is closed is called simple closed curve. So here curve C is closed and it does not intersect itself. So this is one of the example for simple curve. Next, multiple curve. A multiple curve is cross itself. If the curve is start a point and it is go through like this and it is cross at one point, again we can get the region like this. So this type of curves are called multiple curves. Here two regions are, curve is one but regions are two, so that's why this curve is called multiple curve. And connected region. A region is said to be connected region if any 2 points of a region R can be connected by a curve lies entirely within the region is called connected region. Next, simple connected region. The region which can be connected to a point without crossing it is called a simple connected region. For example, square, circle, this type of curves are called simple connected regions. Next one is multiple connected region. A region which is bounded by more than two curves is called a multiple connected region. So for example, if you take a curve C2 and it is in clockwise direction and start at A and at A and it is connected by AB to the region C1, it is in anti-clockwise direction. So here two curves are connected by AB. So this type of curves are multiple connected regions. This is the region, this is also one of the region, and C1, C2 are the curves. And here also the curve C is only one single curve, but the regions are two, R1 and R2. This type of curves are called multiple connected regions. And now we will discuss about our main topic, Cauchy's integral theorem. The statement of the Cauchy's integral theorem is, if a function f of z is analytic and f dash of z is continuous at each point inside and on a closed curve C, then integral C f of z dz is equal to 0. All of you know the definition of analytic function. F of z is analytic, then f dash of z naught is exist in the neighborhood of z naught. F dash of z is continuous means f of z is equal to u plus iv, then four derivatives for f of z, that are dou u by dou x, dou u by dou y and dou v by dou x, dou v by dou y are all continuous. So these main points are in the statement, that are f of z is analytic, f dash of z is continuous at each point inside and on closed curve C, then integral C f of z dz is equal to 0. Let us go to the proof. Let f of z is equal to u plus iv, z is equal to x plus iy, dz is equal to differentiation of z is dx plus I dy. Now we can substitute in integral C f of z dz is equal to integral C u plus iv into dx plus I dy. Integral C u dx minus, we are multiplying these two functions. As usual, separate the real and imaginary parts. So we are getting u dx minus v dy plus I into integral v dx plus u dy. This is called equation 1. Since f dash of z is continuous, we already discussed, if f dash of z is continuous, these four derivatives are also continuous in the region R enclosed by the curve C. So now we are applying the Greens theorem and solve this equation 1. So what is the Greens theorem? The Greens theorem is, if S is a closed region in xy plane bounded by a simple closed curve C, and if M and N are continuous functions of x and y having continuous derivatives in R, then integral, closed integral over C m dx plus n dy is equal to double integral over over S dou n by dou x minus dou m by dou y dx dy. So now equation 1 becomes 2, means in the RHS part, two integrations are comparing with the LHS of Greens theorem is, here it is in the form of m dx plus n dy. M is u, n is minus v. This is also m dx plus n dy form. Here m is v and n is u. So this is equal to, and the first integral we can get double integral over r. N value is minus v and m value is u. So that's why we can get minus dou v by dou x minus m is u dou u by dou y dx dy plus integral. So in the second integral part, u value is n is equal to u and m is equal to v. So that's why we can get dou u by dou x minus dou v by dou y dx dy. This is equation number 2. Again we are using the Cauchy-Riemann equations, CR equations, because of f of z is analytic, u and v satisfies the CR equations. That equations are dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. Now here we are substituting minus dou v by dou x is equal to dou u by dou y. Dou u by dou y minus dou u by dou y is 0. And here also we are substituting dou u by dou x is equal to dou v by dou y. Dou v by dou y minus dou v by dou y equal to 0. Then we can get integral Cf of z dz is equal to 0. This is the proof for the Cauchy's integral theorem. Next theorem is Cauchy's theorem for multiple connected region. So that is, the statement is, if f of z is analytic in the region R between two simple closed curves C1 and C2. Here the region is between two simple closed curves. If f of z is analytic in the region R between two simple closed curves C1 and C2, then integral C1 f of z dz is equal to integral C2 f of z dz. We have to prove this statement. That is, now we are introducing the cross cut AB between C1 and C2. So here if f of z is analytic, then integral Cf of z dz is equal to 0 from Cauchy's theorem. From above theorem, we are taking the equation integral Cf of z dz is equal to 0. So this is a multiple connected region. This is a totally one region or one curve. That's why we can consider as integral Cf of z dz is equal to 0. After that, we can go to where C1 is a simple closed curve consisting of AB and it is in the anti-clockwise direction, where C1, this is a curve C1. First we have to start the C1 in anti-clockwise direction, stop at A and go through with AB. It is a cross cut to the C1 and C2, and C2 is go with clockwise direction. So C1 is anti-clockwise direction, C2 is in clockwise direction. Curve C2 is in clockwise direction and consisting of BA. From equation 1, so our curve C is divided as a 4 parts. First one is integral AB f of z dz plus integral C2 f of z dz plus integral BA f of z dz plus integral C1 f of z dz equal to 0 from equation 1. Means first we have to take the integration of AB and integral of C2 plus integral BA plus integral C1. So our region is, or our curve is divided as a 4 parts, that is AB, C2, BA and C1 equal to 0. So reversing the direction of the integration around C2, because of C2 is in clockwise direction, we can change into anti-clockwise direction. So integral AB and integral BA cancel each other. Now integral C1 f of z dz minus, because of we are changing the direction of C2, so that's why we get the negative sign, minus integral C2 f of z dz is equal to 0. Therefore integral C1 f of z dz is equal to integral C2 f of z dz. So we proved this theorem by using Cauchy's integral theorem. Note, if C1, C2, C3 be any number of closed curves with C, then integral C f of z dz is equal to integral C1 f of z plus integral C2 f of z plus integral C3 f of z dz plus so on. Means that the curve C having any number of closed curve within that integration C is equal to how many number of curves are exist inside that C, that sum is equal to the integration part of C f of z dz. So that's why we can call integral C1 f of z dz plus integral C2 f of z dz plus integral C3 f of z dz plus so on. Next, again we will discuss one more note. Integral, let C be a simple closed curve and let f of z be analytic on and within C everywhere except at z is equal to a. Now first we have to take one curve C, that is simple closed curve. So this is a simple closed curve C. It is analytic everywhere except at z is equal to a, means the center of the region curve is a. Enclose z is equal to a within a small circle with center at z is equal to a and radius r. Let C1 be mod z minus a is equal to r. Means again we have to take the another curve in C, that is C1, center at a and radius is r. So that circle is right as mod z minus a is equal to r. Because of this is indicated z is equal to a, means the center of the circle is a and radius is r for circle C1. This circle is drawn inside the C and center is a. Then f of z is analytic everywhere on and within C and on and outside the C1. So here f of z is analytic everywhere on and within C, on and within C and on and outside the C1, on and outside the C1. So the shaded region f of z is analytic in the shaded region only. So hence by the above note, then we can write integral C f of z dz is equal to integral C1 f of z dz. So what is the above note? C is having how many number of inside, how many number of curves are there, then summation of that integration equal to the integral C f of z dz. Here in this region we have only one curve, that is C1. So that's why integral of C f of z dz is equal to integral of C1 f of z dz. And that's all. Next example, evaluate integral C e power 2z by z minus 2 dz where C is mod z is equal to 1. So mod z is equal to 1 is a circle with center at 0. Here z minus a is a center, but here only z is there, so a equal to 0. So it is a circle with center at 0 and radius is 1. So now first we have to draw the circle with center at 0 and radius are x-axis, y-axis and center at 0, 0 and radius is 1 unit. Then we can draw the circle. Now the point z is equal to 2 lies outside the C. What is the 2 here? Z minus 2 equal to 0, z is equal to 2. This point is lies outside the C. So the given region is mod z is equal to 1. Our given point is outside the C. So then the function f of z is equal to e power 2z by z minus 2 is analytic within and on C. So by using Cauchy's theorem, what we have to say, f of z is always analytic within and on C, but our point is outside. So that's why we can write by Cauchy's integral theorem, integral C e power 2z by z minus 2 dz is equal to 0. Directly we are using the Cauchy's theorem and analyticity of the given function, then we can write the integration value is 0. Next one, prove that integral c dz by z minus a equal to 2 pi I, where c is modulus of z minus a equal to r. Here center at a and radius is r to the given circle. So how to find the center? Z is equal to a, x plus iv is equal to a, x quadrant is a, y quadrant is 0. So that's why I'm identifying the point on x-axis a comma 0, and radius is r. So that's why I'm taking r units and draw the circle center at a comma 0. So here I am taking the point center, the point is a, and any point on curve z, that point is called p. So that's why we consider actually then it is AP, means a straight line. So AP equal to, from point z to a, how to calculate the z to a? Z minus a is equal to AP. So this point is called A, this point is called P. So that's why AP is equal to Z minus A. Let AP make an angle theta with x-axis. So with the x-axis, AP is making the angle theta. So parametric equation of z at center 0 comma 0 is z is equal to r e power I theta. Already we discussed in the polar form of Cauchy's integral, Cauchy's Riemann equations. So that's why z is equal to r e power I theta is a parametric equation for the z at center. So by using this parametric equation we can solve this integration. So here AP is equal to r e power I theta. So AP means z minus a is equal to r e power I theta. So dz is equal to differentiation of this equation, dz is equal to r with respect to z. So we are differentiating, so that's why r is a constant here, keep like that, and e power I theta integration is I into e power I theta d theta. This is the parametric equation to the circle C, and theta varies from 0 to 2 pi, r being constant. So integral C dz by z minus a is equal to integral 0 to 2 pi r I e power I theta by r e power I theta, because of z value is r I e power I theta into d theta. Z minus a is equal to r e power I theta. So r cancel, e power I theta also cancel, I is constant right outside. Integration of d theta is theta, limits are 0 to 2 pi. We get upper limit is 2 pi minus lower limit is 0, 2 pi into I, 2 pi I. So next one is very important one. Show that integral cz plus 1 dz is equal to 0, where c is the boundary of the square whose vertices at the point z is equal to 0, z is equal to 1, z is equal to 1 plus I, z is equal to I. First we have to draw the region to the given vertices. So first you can take x-axis and y-axis. First point is z is equal to 0. Z is equal to 0 means we are comparing with x plus iy is equal to 0. X quadrant 0, y quadrant 0 means it is a point 0 comma 0. Next one, z is equal to 1 means x plus iy is equal to 1. X quadrant 1, y quadrant 0, 1 comma 0. So first curve is O to A, that is 0 comma 1 comma 0. Next one is z is equal to 1 plus I. Then we can comparing with x plus iy. X plus iy is equal to 1 plus I. X quadrant 1, y quadrant is also 1. The point is 1 comma 1, that is called B. So now we can draw A to B one line. So next one, z is equal to I. Z is equal to I means x plus iy is equal to I. X quadrant 0, y quadrant 1. we are identifying all 4 points to the given regions. 0, 1 is the last point. Now our region is divided as 4 parts because of this is a curve, but dividing as a 4 parts, it is not possible to find overall integral CF of z dz directly. It is divided as a 4 parts, so that's why we can write the integration is also 4 parts. That is, I is equal to, I am taking I is equal to integral C z plus 1 dz. Now overall integration I need, so C, the curve C is divided as a 4 parts. That is, first curve is OA, next curve is AB, next curve is BC, last curve is CO. So along these curves we can find the integration. First one is IOA plus IAB plus IBC plus ICO. So now here the first point is 0, 0. Next along first point is on OA. So first point is 0, 0 and next point is 1, 0. It's a clearly x varies from 0 to 1 and y is equal to 0. So because of y quadrants are zeros, so that's why y is equal, it's a clearly we know that on x-axis y is equal to 0. So that's why y is equal to 0. X varies from 0 to 1. So x varies from 0 to 1 and y is equal to 0. So what is z value? Z is equal to x plus iy. Y 0 means z is equal to x. Dz is equal to dx. So IOA equal to integral x is equal to 0 to 1. Z value is x. X plus 1 dx. X integration is x square by 2 plus integral dx is x. Limits are 0 to 1. 1 by 2 plus 1 value is 3 by 2. Next on AB. On AB. So here it is a ordinate x is equal to 1 and we simply identify the x quadrant value is 1 on both the points. So that's why x is equal to 1 and y varies from 0 to 1. So on AB x is equal to 1 and y varies from 0 to 1 and z becomes 2. X plus iy is equal to 1 plus iy. Then dz is equal to I dy. Going to the integration, integral 0 to 1 plus, because of y varies from 0 to 1, integral 0 to 1 plus iy plus 1 into I dy, because of dz value is I dy. Then here 1 plus 1 2 and iy, 1 I is extra, so that's why that is constant right outside. Integral 0 to 1 2 plus iy dy. So integration with respect to y, 2y plus I into y square by 2. Limits are 0 to 1. I into 2 plus I, if you substitute the limits, we are getting the value 2 plus I by 2. Multiplying with I, we get 2I minus I into I square. I square value is minus 1 by 2. Next on BC, x varies from on BC. Then here BC x quadrant values are 1 2, means x varies from 1 to 0. So here on this curve y is equal to 1. Simply we can identify from the point, so that is y quadrant value is 1 on both the points. So that's why we can write y is equal to 1. X varies from, we are taking the region of BC, so that's why curve of BC, so that's why we can start the limits from 1 to 0. So on BC x varies from 1 to 0 and y is equal to 1. So z becomes to x plus iy and dz is equal to dx. Substitute in the integration 1 to 0 x plus iy plus 1, because of z value is x plus I and f of z is z plus 1. So that's why x plus I plus 1 dx. So then we can write integration. X integration is x square by 2. 1 plus I is constant. Integral dx is x limits are 1 to 0. So upper limit becomes to 0 minus lower limit is 1 by 2 plus I plus 1. So that is minus of I plus 3 by 2. Next one, last one on CO, y varies from 1 to 0 and x is equal. On y-axis clearly it is x is equal to 0. So y limits are from 1 to 0. Then y limits are on y-axis x value is 0 and y limits are start from 1 to 0. So that's why we can take y is equal to 1 to 0 and x is equal to 0. Z becomes to I y and dz is equal to I dy. So ICO equal to integral 1 to 0. So Z value is I y plus 1 into I dy. I write outside integral 0 to 1 I y plus 1 into dy. Integration with respect to y square by 2 plus y limits are 1 to 0. Upper limit becomes to 0. Lower limit is I by 2 plus 1. So we are multiplying with I. Then it is minus I square by 2. Here minus into 1 minus and I multiply I. So I square value is minus of minus plus 1 by 2 minus I. Finally, we can add all four integral values to get the I equal to IOA plus IAB plus IBC plus ICO. So IOA value is 3 by 2, AB value is 2I minus 1 by 2 minus BC value is I. Because of IBC is a negative value, so that's why we can write minus I plus 3 by 2 plus last value is 1 by 2 minus I. So cancel all the values, we are getting the solution is 0. What is the I? I is equal to integral Cz plus 1 dz. Value is 0. This problem is proved by using multiple connected region. So that's all, students. In the next class, we will discuss about Cauchy's integral formula.